Okay. Online.
Okay, so let's start, everyone. In the last few lectures, we discussed a bit how to extract observables. In particular, we focused on this deflection or deflection angle from amplitude techniques. We discussed in particular in some detail the iconal exponentiation and this saddle point that allows us to calculate the angle from the derivative of the iconal, and then we compare with the KMOC or observable-based formalism, which eventually led us to the same result. And last time we concluded with some remarks about unitarity and how we can use the unitarity of the S matrix to calculate some portion of our answer, and in fact deduce from it the radiation reaction at two loops. What I did throughout these lectures up to now was to pretend that we know how to calculate all the integrals that we encountered, and of course at some point I have to pay the price for this and show you actually how we go about doing this, at least in some examples. So today, what I decided to do was to outsource all the integrals to this lecture. So today is going to be a bit technical. So we are going to discuss how to calculate some integrals that are relevant for our problem. And in particular, this will serve as an occasion to be a bit more precise about this argument that we've been using throughout. You remember we were often saying we are interested in a regime in which the momentum transfer is small, and therefore we are restricting to a region of integration in our loop integral in which the loop momentum transfer is of the same order as the momentum transfer of the whole process, and this eventually gives the right result for our purposes, but this is going to be the first topic I want to illustrate, so this method of regions. So the idea of this technique is the following. Often you encounter in particle physics problems, or in general in any problem that involves integrals, particular Feynman integrals, the following problem. You know that you're interested in the result of your integrals only in a special kinematic regime. For us, it's going to be the small momentum transfer regime, which involves the external momenta. But of course, what you don't want to do is first evaluate the integrals for generic kinematics and then take the limit in the kinematic regime you're interested in. You would like to anticipate this as soon as possible. So this is what this method of region does for you. And to illustrate it, let me focus on one loop example. This is going to be our box integral, scalar box integral, which, okay, remind you, my favorite labeling for external momenta. So let me write it down at least once in full glory. Minus 51.n plus squared minus I epsilon 2p2.l plus squared, and then the massless minus L squared and minus Q squared. And I'm going to use some shorthand notation for the loop momentum measure that, well, it's such a way to get rid of some factors of my prime. So, I mean, as we were saying, this is going to be a function of the masses and of the momentum invariants that we can construct, so S and T in particular. But the issue is that we only want to calculate this in the small q regime. So we care about regime in which, say, roughly speaking, P1 and P2 are big compared to Q. So maybe the other direction. Q, the momentum transfer is much smaller than P1, 2. Of course, this is a bit of a hand wave writing because these are momentum, so momentum which are components, more precisely, squared is much smaller than the masses squared, and the mandatory invariant sigma is generic. But I hope this writing is sufficiently clear. So in particular, what we are tempted to do is to simply Taylor expand this integrand in small q, but then what you immediately see that you need to decide what to do with L, right? To do momentum, which is principle integrated over the whole space. So the idea is to divide the integration into two regions. The first is the one in which the momentum transfer is indeed much smaller than this P1, 2, which are generically of the same order as this momentum in the loop momentum. So this is the so-called hard region, because the momenta, well, the loop momentum is hard, as energetic as the massive particle. And then, of course, there is another region, is another possible choice in which L scales of the same order as the momentum transfer, and these are both much smaller than each. Not surprisingly, is solved. So let's do it. Where we can approximate the result as follows. So let me adopt some notation. Hard meaning that we split. Formally, one should introduce a scale lambda, which is intermediate between Q and P, and say that the hard region is the one in which momenta are bigger than lambda, one is smaller than lambda. I hope this is sufficiently clear. This is the hard region distribution. So in this region, what we can do is indeed expand for small q, right? Because L is much bigger than Q, so we can, for instance, neglect this Q here, and the other propagators remain as they are. L squared squared. And then there is this contribution from the soft region, in which the situation is opposite, right? L is of the same order as Q, so we cannot expand this denominator. Instead, what we can do is that we can say, look, L is of order Q, so L squared is of order Q squared, while P1 dot P2 dot L, say, is of order Q. So these L squared are very small compared to this, so we can neglect this L squared over here. So the bottom line is minus 2P1 dot L, 2P2 dot L, and then the other two, we leave them as they are. Okay. Now, what we gain in this step is that we simplify the integrand, right? So these are slightly simpler functions than the original one, but we introduced a complication, the fact that there is a cutoff in our integration. This we don't like, right? Because dealing with integrals over the whole space is much easier than integrals with respect to some subregions. So the sort of trick that this technique employs is to add and subtract the pieces that are missing from these two contributions in order to re-extend them to the whole space-time. So we are going to add back the integral over the soft region of the hard region integral and the integral over the hard region of the soft region integral. So let me do it and then comment. So let me introduce IS and I hard and I soft, which are the integrals re-extended over the whole region. So of course, the I epsilon prescription is always implicit in. And then we have to pay the price of this, namely subtract, as I was saying, this. So integral over the soft region and the integral over the hard region on the soft region. Up to now, I mean, I didn't do anything. Now the magic happens in the following way. now we can say, okay, but now look, you are integrating this thing in the soft region, but in the soft region, L squared is small with respect to P at little L, so we can neglect these guys to leading order, and vice versa here. Now we are integrating this in the hard region, and in the hard region, L is very big compared to Q, so we can neglect squared. We can neglect Q here. So you see this recombines as I box soft plus I box hard minus the integral. You see these two are now the same, so we can simply recombine this as an integral over the whole space. Right. And now you remember that since we have been working in dimensional regularization, this is simply 0 because this is a scale-less integral, right? If we scale L by some lambda, this will just come out as a factor lambda to some power. So this is identically 0 in dimensional regularization. Okay. So basically, you see, to leading order now, because we've been expressing, of course, what we should do if we want to go to subleading order would be to expand in these two scaling regions, both this object, and the magic will continue happening. But to leading order, we just check that what we can do is what, well, your math teacher told you cannot do usually, which is bring the limit inside the integral sign and simply forget about the fact that the integration is over the whole space in both cases. The price that you have to pay is that you have to consider all the scaling regions. In this case, we only have two, which give non-trivial results. In this case, there is the soft region and the hard region. But I emphasize again, the scaling limit is expanding this according to those rules, but the integration is over the whole space-time. So these are vanilla Limreg integrals with these simpler denominators. Okay, so this is already something better. There is a further simplification in our case, namely the fact that, remember, we only care about non-analytic contributions in Q squared in particular. So clearly, this integral, we don't really care. Yeah.
Yeah, another question.
Yeah.
If I start on the expression here on the upper right, so when you split into two domains, so if I do that, I would expect maybe that the result I'm going to get will be correct up to a factor for the unity. No?
Yeah, exactly.
Doing some hard splitting.
Exactly.
So at the border,
so indeed,
I assume it will be dominated by the boundary. There I'm making error of factor 1.
Yeah, to estimate the error, as I was mentioning, you should go to subleading order. So in fact, maybe let me come back to this in a second because I was just about to estimate at which order these two things start. So this one, well, this one doesn't depend on Q. Hard. And then it would only receive corrections that are powers of Q squared. So even so it could be, this would be a delta function when you go to impact parameter space, and then there would be derivatives of delta function, so we don't care. And the other one instead, let's count. So there is a 4 that comes from the measure, and then -1, -1, -2. So the 4 goes away, -2. So my S box will make 1 over Q squared, or more precisely, if you remember that D is not equal to 4, is 1, 4 minus 2 epsilon, 1 minus epsilon plus corrections. So indeed, the soft region is the one to care about. Now let me come back to Patrick's question, which is a good point. Is there a way of seeing already from here, right? This is the question, what mistake we are making? Yeah, it's not obvious a priori, right? Because it seems that only when you recombine the two, you get something that is nice in Limreg, and then you can throw it away. Instead, separately, I suspect it's a bit complicated because of these cutoffs. It's not clear how the cutoff surface in momentum space introduces an additional dependence on Q. You agree, right? Because in principle, you can apply the same counting that we just did to these two integrand, and then you would be tempted to conclude that this is of order 1, as you were saying, and this one is instead of order 1 over Q squared. But that cannot be correct, because we know that when we recombine, they cancel in the right.
Well, actually, this is the second integral, the one which this one. So if you put this at cutoff, by the same argument I gave before, it will be logarithms of the rest of the cutoff.
Exactly, there are logarithms.
So, but then the value of cutoff, it's up to you. You choose the way you like. So therefore you could choose cutoff being Q squared, then the second term goes away. You left over the first.
Yeah, but I would say it's not easy to see at first sight what the precise scaling of both integrals are. Would you agree with that?
Scaling with
respect to Q. I mean, just by power counting, it's not particularly obvious. I hadn't really thought about that, because this is somehow the.
No, but sorry.
Yeah.
If you just think only about second integral.
Yeah.
So it depends on three moments: pi, pi j, and q.
Yeah.
And it has additional invariance under the scaling of pi and pi j. So therefore, by definition, you could write it like 1 over q squared certain power or some dimensionless function on the ratio pi, pi j.
And then there is the cutoff.
Yeah, but by dimensional argument, you could basically write the more general expression for the second integral up to some function.
Yeah.
Dimensionless function of the ratio q squared over the cutoff.
Okay. So
this integral will be like 1 of pi q, pi j q. Yeah. And there's two pi j.
Yeah.
So this should be arrow prefactory because integral has scaling under respect to pi j, which should be preserved. And there is possibility to have pi I times pi j.
Although it's a bit tricky, right? Because pi, maybe let's not too much, but p1 dot q is equal to 1/2 q squared, because we are on shell. So
Even better. What about pi I pi j?
Pi j is our sigma up to some factors of the masses. So sigma is p1 dot p2.
But now you see that if you start to combine this quantity, you have to construct something which is invariant under scaling pi I pi j. It's the only quantity which we construct of pi I times pi j divided by pi I q pi j q.
Maybe in the interest of interesting, but it sort of shows that it's not as easy in order the fact that we are discussing it. Thanks. So exactly. So this is a bit the idea. In the end, this is to justify the fact that we are always restricting to the soft region, because the hard region contributions are analytic in Q squared. Thanks to this one, I can select. Maybe another comment before moving on is that a similar argument we also apply to our Fourier transform, right? Remember, at the very beginning, we said, we are interested in large B, and therefore we can restrict our Fourier transform integrand to and evaluate it to small q. So I mean, this is again very familiar to all of us, because we are familiar with Fourier transform and how they behave. But in a sense, this can be also seen as an application of this method of region. In particular, well, let me leave it to you as an exercise. You can indeed show that, for instance, as an exercise, you can check the Fourier transform of this function. This is just a very simple example, but just to convince oneself. So this, let me call this f q. Then you remember there was the tilde, it was our Fourier transform. F tilde. This one is a case in which you can perform it exactly without neglecting this q squared with respect to m. You can find it. The result is actually for E 1 over 2 pi. There is a divergence. We are in for D. Log of B divided by some B0, which involves some pi, some Euler gamma. You can work this out. And then there is Bessel function of modified Bessel function of the second kind, K0 of the dimensionless combination B times M plus order epsilon. And you can check that the same conclusion holds when applying the method of region, in the sense that if you're now interested in the limit for large B of this expression, what happens is that you can restrict to the soft region here. So in practice, consider Q of the same order as 1 over B and therefore neglect it with respect to n. And then here what happens is that you see that this is exponentially suppressed for large values of Bn. Oops. Suppressed. So this is a sort of an aside. But just to say, also the fact that we are restricting to a small q when doing the Fourier transform is another application of the method of the region. In fact, here only the soft region contributes, and the hard region is exponentially suppressed.
So now,
Yeah.
now when you mean soft, you mean q goes to 0.
Yeah. Now exactly. Now the integral in respect to q, right? So the soft region would be then q is of order 1 over b, and they are much smaller with respect to m, because now q is the integrated variable. There is a bit of a change of notation. And the hard region would be when instead q is of the order m, and they are much bigger with respect to 1 over b. But this, I mean, you can sort of see it from here that this is a very exponentially suppressed thing, because these things oscillate wildly when q is much bigger than 1 over b.
No, so just on the blackboard, maybe there's a typo. I think you wanted to cross q squared instead of m.
Ah, thanks.
This,
Sorry. Like this. Thanks. Okay. So, yeah, this was just to justify a bit the logic. Then, what I wanted to do is to illustrate a bit some of the techniques that are involved in the, let's say, pipeline. Suppose you are faced with an integrand that someone provided you, that you calculated with some method that we discussed a bit, like generalized unitarity or double copy. Then you want to evaluate, in principle, all the integrals that appear in your integrand. In principle, you can apply this discussion to all the terms in your expansion, but there are actually better methods. And so let me just sketch the general sort of general strategy to attack on such problem. So the idea is the following. So now we know that we only care about the soft region, but still we have work to do. So the one step is to use integration by part identities that link these different integrals to one another and identify a basis. It's actually convenient, as has been noticed in a paper by Julio Parra Martinez, Michel Ruff, and Mao Zeng, to first expand in the soft region and then look for a basis of master integrals. So reduce the soft integrals in your problem to a basis. Let's say some vector of integral 1, 2, which are often called master integrals. This basis, I mean, as all basis is not unique, so you cannot just say the master integral of the problem R, and it is my master integrals of the problem R the one that you choose. So there are various softwares that help you doing this too, that are particularly popular and easy to use are LightRef and IPhT by in our applications, eventually, for instance, just to have an idea, one loop, which is the example we will be focusing on in order to do things that are Blackboard friendly, there are just 3 master integrals. At 2 loops, if you organize things in this way, there are about, well, of the order of 10, 20 master integrals, although some repeat themselves and never actually check. And there are more clever ways of organizing the problem, which are simplified. But this is just to give some numbers. And then once you have a basis of master integral, the idea is to take derivatives of these master integrals with respect to the invariant. In our case, there will be only one invariant, which is related to this sigma And of course, the derivative of a master integral is an integral which you can re-expand in the same basis. And in this way, you can derive differential equations. In our case, ordinary differential equations. For the master integral. So in fact, let me introduce some notation that I forgot to introduce. Let me do it. You remember, in order to consistently expand from small q, it's convenient to introduce these barred variables that we had last time. For instance, p1, q minus and 1 bar, u1 plus 1/2 q, etc. For the other ones, let's not repeat all of them. And then it's convenient to use these variables instead of the ones defined with respect to the incoming momenta. So the notation is the following. Y is the dot product of the two average velocities, let me call them like that. X is related to y in this way, rationalizing some square roots that appear here and there. And well, for my own convenience, I will also introduce this additional parameter tau. So in this case, the differential equation will take the schematic form d. So the master integral will be functions of this x, which is related to y, which in turn is related to sigma. It's sigma plus order q squared corrections. And of course of the dimensional regulator. And there will be, in general, a complicated matrix which depends both on the dimensional regulator and on the x times this vector. Then when expanding around equal 4, it's convenient to look for a particularly smart choice of these master integrals of this vector that puts this system in a nice form, which is a form in which the dimensional regulator only appears in a certain way. So smart choice is the choice of I such that there is some sum, or some roots. In particular, in our case, it will be 0, plus, and minus 1. Some matrices which are numbers, matrices of numbers like 3, 1/2, something like that, times b log x minus this xj. And the reason why this is a smart choice is that since we are only interested in resolving this problem for small epsilon, we can solve this problem perturbatively. In particular, we can find the order n plus 1 in the epsilon expansion by simply integrating with respect to x the order n in the small epsilon expansion of the y's against this d log, which leads to polylogarithms. Okay, here there are many caveats. For instance, you could ask, is it guaranteed that you can always do that? Are they always going to be polylogarithms? Well, the answer is no. But if you can, this is very powerful because you basically trivialize the problem up to one thing, which is fix the boundary condition of the differential equation. And in order to do that, a popular choice is to look for an expansion of the integrals for small x, for x close to 1, which means small velocity. So in the near static limit. Expand. So you basically fix the boundary conditions as x tends to 1. So this is a bit the schematic pipeline. And what I wanted to do in the remaining time is to, well, illustrate this in some detail for the simple case of the one loop box integrals that we a minute ago. Of course, I should emphasize that everything I'm saying today for the box is completely overkill because the expression for the box is known. So you could just as well forget everything and just take the expression and expand it. But somehow the idea that what I'm saying is useful when, for instance, in the two-loop example and also beyond, in which the expressions for the generic kinematics integral is not known, and then you only care about this small momentum transfer limit, or more precisely the soft region. So, are there any questions on the general strategy? Yeah.
Sorry, I missed it. What is epsilon?
Epsilon is the dimensional regulator. So,
Okay.
Xj are numbers. It depends
J are
on.
numbers. In our case, it will be really just 0 plus and minus 1. You can, well, basically guess them from the singularities of the problem. I mean, for instance, 1 is going to be this singular limit in which the velocity tends to 0. And in fact, another trick to fix some of the boundary condition is to realize that x equal to minus 1 should not be a physical singularity. And this already introduces some constraint among the possible boundary conditions that you have, so simplifies your life. There is a very nice discussion on this in the paper I was mentioning by, another paper by Herman, Paramartinez, Rupp, and Zhang in 2021. 2021. So, yeah.
But so these boundary conditions, you evaluate them explicitly by setting x equal to 1, and the integrals are very easy. What do you do?
If you think about it for a second, I think you can come up with the answer to that by thinking about the first half of this chat that we had. So we are looking at a Feynman integral, and we want to evaluate the limit in which a kinematic variable is sent to a special value. So what should we do? We should apply the method of regions. However, now with respect to this parameter, so in fact that's what I want to do, is to evaluate the limit as x tends to 1 before evaluating the full thing, because otherwise you wouldn't know it. It's exactly the same problem, but now the kinematic variable is x. So we are going to distinguish two regions in particular, sort of ordinary region in which you do exactly what you said, you just set x is equal to 1, but sometimes that's not the full thing. You have to do a sort of more refined scaling.
And so when you do this method of regions for computations, I mean, okay, more regions emerge, I guess,
Exactly,
but the story is not complicated.
No, essentially the idea is that there are two sort of scalings that you can assign to lines that you have. One is if they are not supposed to go on shell, and the other one is if they can go on shell. What you can have is that the more loops you have, the more lines can go on shell, so you have more combination of people sometimes say potential and radiation modes. So for instance, at one loop you will only have potential, but the two loops you can have potential and radiation. At three loops you can have potential, radiation, radiation, potential, potential, radiation, potential, 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 and things complicate in a similar way. Okay, so let's try to do this in some detail. And yeah, our case study is going to be this box, so let me introduce some notation just to be explicit. A1, A2, A3, A4. The family that we want to study are these four denominators that I just erased. And these are just to be this is classes. Okay. So and well, drawing is 1, 2, 3. So in fact, let me leave to you as an exercise and evaluating the simple ones. So if, the idea is that when you have a maximal topology, like in this case the box, typically the master integrals associated with this family will be the top topology and possibly some pinchings. So the ones in which you eliminate some of the propagator. In this case, you can have, for instance, this triangle thing, which we pinch line number 1, or we could have a bubble, which we pinch both line number 1 and line number 2. We could think of pinching 3 and 4, but this, as you can easily see, would lead to scaleless integrals, and this is reflected in the fact that the contributions would be analytic, so they do not give any contribution to the soft region. Yeah.
What do you mean by maximal topology?
Yeah, just in this case, the thing with all the denominators. You know. In some more complicated examples, you could have some denominators and also some irreducible numerators. So some things that you have to add here in order to make this a basis. Say, but in the one loop, you never have it. Okay. So the easy ones are this one, and the reason is that they do not depend in any non-trivial way on this parameter x. So, for instance, for the G0, 0 alpha beta, you can show that the result is gamma of alpha beta minus 2 plus epsilon divided square alpha minus 2 plus epsilon. And then there is another combination of gamma functions. Divided gamma. And similarly, if you want to work out the triangle, which is gamma 1/2 plus epsilon divided by 2 squared 1/2 plus epsilon times square root of pi gamma 1/2 minus epsilon squared divided 2 gamma 1 minus 2 epsilon. Right, so this is an exercise for you when you don't know what to do. Instead of doing a pseudo. Somewhat more interesting case, although it's still elementary, is the box. So read the maximal thing. So for that one, let me call it, let me give it a name. So for that one, we can still evaluate it directly. In this case, as I said, everything is very simple, but let me do it in two ways. First, evaluating it directly because we can, and then pretending we don't know it and trying to use the pipeline we just said. So here again, it's a very simple exercise. You can use your favorite parameter representation. I like Schwinger parameters, but it's up to you. You should be able to find that when you integrate over, say, the Schwinger parameters associated to line 1, line 2, line 3, and line 4, you can factorize the two integrals by rescaling those associated to lines 3 and 4 by the ones associated to 1 and 2, and the result is the following. So again, some gamma functions come from the easy part. Is in fact associated with the massless line. And then you have another piece which I call IX, is instead this. Plus y. Okay, so basically all the non-trivial dependence on y comes through this integral, so this is what we want to do. Okay, this integral is actually easy. For instance, you can redefine variables in this way, and you will find that, okay, this gives a factor of 1/2 if you calculate the Jacobian, and then this is the integral over t is simply an integral over type e to the minus t times something, so the result is 1/2 integral from 0 to infinity dx of x squared, well, ds s squared plus 2 minus y minus I epsilon s plus 1. And this you can do by partial fraction, right? You can call s plus minus the root of this thing here, so y plus or minus square root of y squared minus I plus the epsilon. And then you can decompose this 1/2 1 divided by s plus minus s minus the integral from 0 to infinity ds of 1 over s minus s plus minus s minus s minus. These are logarithms, so you get 1/2 s plus minus s minus, and then you have the log of minus S plus evaluated as 0, so with a minus because it is a lower, and this with a plus log of minus S minus. Okay. So then we have 1 over 2, 1 over twice the square root that comes from the S minus plus minus S minus, S plus minus S minus. And then here, okay, this is the hard part. So here we have a minus. And then we have a log of minus S plus. S plus has a plus I epsilon, so we are slightly above the negative real axis, which I think this means that this has plus I phi. So let me do it. So this root is this is a slightly positive imaginary part. It's plus, but then it has a minus, it has a slightly negative imaginary part. It is really minus I phi, but it has a minus here, plus I think. And then there is minus log of the real part of this. So which you can show it's actually arc cosh of y. And here the charade is a bit different, but so plus, but this is minus S minus, so minus times minus is plus, which means that it's again I phi, right? And plus log of S minus, you can show that the log of y minus the square root is minus arc cosh. So another factor. Yeah, I think we got this one. Minus cosh. Well, actually, you need to use this other thing. So log of x, x is precisely this y minus, so this should be the final. Now, let's say it's a very simple example. You can do everything, but suppose we didn't know how to do this last bit of the derivation, and we were maybe the first line. What do we do? How do these differential equations help us? So the idea, as I was saying, is to first come up with a smart choice of basis that puts the system in a nice form, and then to evaluate the boundary conditions. So let's try to do this before the break. So coming up with the so of course the first natural choice would be to simply say that the top, so the box, the triangle, and the bubble are our master integral. This is a valid attempt. However, by using these programs that I was saying, it's easy to see that the differential equations that come from this choice are not quite in epsilon form. So what are the tricks that allow you to go from a, let's say, naive guess to a better guess? Okay, I'm by no means an expert in this, but one standard trick is to divide by the maximum cut. Divide. In our case, it's gonna be enough to divide by the only cut that you can think of with box, which is this one. So we divide by the two particle cut, which is the following thing. So there is an I just to cancel the 1 over I, the times phi, and I introduced earlier on. So this is the same integral as above, in which you replace these guys by delta function. Okay. And this is actually very easy. You can, for instance, evaluate it by going into a frame where U1 is at rest, so it's 1, 0, 0, 0, and the other particle with some velocity in some direction. Or you can use the composition we used earlier on in the lectures in terms of L parallel and L perp. The result is simply gamma. So what happens is that the integral over the perpendicular components which survive precisely give the same prefactor that you had over there, And then the integral of the longitudinal components here just gives a factor of pi. So pi, and the Jacobian that is needed to go to this L parallel variable, which is the square root of y squared minus 1. So you see, already starts looking quite similar to the true result, except that we are, in fact, what this trick means is that it's a good idea to multiply the result by square root of y squared minus 1. Okay, if you do that, so now let me define the basis that actually does the trick. G. One, 0, 1, 1. So this is the, and as promised, we take epsilon squared times tau, which is the square root of y squared minus 1, notation I'm using, q squared, the box. This is the basis that does the trick. So now we're calling f vector the master integral, we call this from the change. And this satisfies equal to epsilon times the matrix, and this matrix is very simple. So you see, I mean, the first two lines are trivial simply because the triangle and the bubble do not depend on x at all. So of course there are only zeros. And then the nice thing is that the derivative of the box, or more precisely of the box rescaled by this two-particle cut with respect to this log of x, is just proportional to the bubble. So in fact you can solve. Okay, the solution of the first two equations is trivial. Simply evaluate them. This is what we did. For the last one, the only trivial one, and the solution is f3 equals gamma 1 plus epsilon gamma 1 minus epsilon squared. So this comes from the bubble. Since we know the bubble is, it's going to be the bubble times log x, actually. Or gamma minus epsilon log x plus a constant which we need to fix. Okay. Again, here we are pretending that we didn't know how to evaluate. So suppose you are not able to evaluate this exactly, but we know the differential equation. We know that the dependence on x is just given by this log x, which, by the way, we know is the correct answer. And then we only need to fix this C3, which is in practice, since we know the result is going to be just this I pi, but let's see how we can derive it. And this is an excuse to illustrate the mechanism that we were discussing a minute ago with Nicola. So our task is to evaluate, well, f3 as x tends to 1, or tau tends to 0, or y tends to 1 again. So let me do that. Of course, I made a mistake of erasing the integral that I needed. Let me try to do it again. Okay. So now we see, yep.
So in F2, it's Q square or
It's the square root of q squared.
square root? Okay.
Yes, because you remember there was this. By the way, how do you fix these? The q's you can just fix by this power counting that we did in order to make everything scale, say, like 1 over q to the 0, q to the epsilon, q to 2 epsilon. The epsilons you can deduce by looking at the, say, infrared divergences again by power counting the momentum space.
And do you have any intuition why you need a 2, 1 before the guess was a 1, 1?
This is what the program gave me.
Okay.
So actually, after that, doing all this, I also wanted to say that for simple examples like this, there is actually a program that puts the system in epsilon form. It attempts, there is a program in particular called Epsilon by Browser, which does it for single scale programs. There are several others like Kira, Reduce, Initial. They're all slightly different, so sometimes you can just put it, then ask the computer if it has a guess for the epsilon form, and of course, for this simple example, it finds it. But it's completely equivalent to just putting the ones and some other prefactor. Okay, suppose we don't know it, and we want to now evaluate the limit as x and y tends to 1. So let's try to do the naive thing, which is just set y equal to 1. Here you see this recombines into a square. And then we can use variables that are a bit simpler to visualize. So in principle, the integration will be in this region x1, x2 positive, right? We can introduce this rotated alpha and beta. So of course we can rewrite this as the integral. Probably there is a Jacobian, but let me worry about that later. The integral over, say, beta going from minus infinity to plus infinity, d beta, and alpha now goes from the absolute value of beta to infinity, right? So we are slicing the space in this way. Okay. The alpha e to the minus beta squared. Probably there is a factor of 1/2, the Jacobian. But this is clearly badly divergent, right? Because the integral does not depend on alpha, so this is equal. So what is this telling us? It's telling us that we are not looking at the right region, right? So we should not simply put y to 1, and I mean, knowing the result is pretty obvious because it goes like 1 over square root of 1 squared minus 1. But let's try to do something a bit smarter. So you see, the issue here is that when we send y to 1, there is a direction, this 1, 1 direction in x1 and x2 space, that becomes a zero mode of the exponent, right? Alpha does not appear here. So the idea is to, well, one way of doing this is to assign a different scaling to the two variables associated to these two directions. So the idea is to, now we are interested in the limit tau tends to 0, say. Remember, these are all equivalent variables. So we have to enhance the zero mode because otherwise it doesn't appear. So beta goes of order 1, which is fine, but we have to let alpha be of order 1 over tau. So this is a sort of singular region in a sense. And okay, if we do that, let me erase this. So now what we have to do is that we erase also this. So we have to keep the whole exponent, rewrite it in terms of x1, in terms of alpha and beta, and then apply that scaling over there. Then what we find is instead of what I just wrote, we find that there is another contribution. So d beta integral from absolute value of alpha to infinity. There is indeed e to the minus beta, but then there is the piece that we were missing, minus alpha squared over 4 minus tau squared minus a0 d alpha. And you see, indeed, this case is of order 1. So the criterion for choosing a good scaling region is that this thing should not be neither exponentially suppressed nor small, otherwise it would expand it out. So beta is of order 1, and alpha times tau squared is also of order 1. So this is the right scaling. And in fact, to leading order, since alpha is much, sorry, this is beta. Since beta is much smaller than alpha, we can even neglect this lower integration region and set it to 0. Otherwise, we would get something that is subleading, right? So then these two are Gaussian integrals. There is 1/2. The integral over beta just gives us square root of pi. And the integral over alpha gives 1/2 because it's half the Gaussian integral times the square root of 4 pi divided by minus tau squared minus a0. and this is precisely 5 divided by, and then there would be e to the minus I pi half, so e to the plus when we put it in the numerator. And I forgot about this one, I forgot. Yes, 2, and then 3. And tau, you remember, is exactly square root of y square minus 1. So, put it in order, maybe the limit should go here. Very good. So, this is indeed the missing constant part, right? Because now if you multiply by the tau over there, this cancels, and this gives us precisely the constant that we were missing, and you can check that it's exactly the one that we obtained by direct evaluation in this simple case. So maybe before the break, let me conclude by giving an exercise again, case which is slightly less trivial. So the same exact logic can apply to another integral, which is instead relevant for the two-loop calculation. In particular, this guy over here. This sort of N diagram. Maybe let me give just relevant pieces of information. So, of course, you can write down some soft integral, soft region, sorry, integral for this. It's similar to the one we had, but now with two loop momenta, 1 and the 2. Okay. And you can reduce it by your favorite parametric representation to the following form. Where we introduce the following notation. Big T is T1, T2, plus T2, T3, plus 3, T1, and the yxt is close cousin of the yx that we had above, with an important difference. Yeah. And okay, the difference is that now, as you can see, the two integrations are not factorized. So there is an integration over 1, 2, 3 here, and an integration over x1, x2, sorry, t1, t2, t3 here, x1, x2 here, but t1, t2, t3 also appear as coefficient in this quadratic polynomial in the exponent. However, it doesn't really change much in the sense that what you can do is, instead of evaluating first the t1, t2, t3 integrals, you can first evaluate this for small tau or y equals to 1. So of course, what I'm not telling you is how to derive the system of differential equations. That is another story. You can use the program I was mentioning, for instance, epsilon. Now the issue is evaluate this for tau tends to 0, so small near static limit. In this case, there are two contributions. One ordinary contribution, in which you simply set tau equal to 0 or y equal to 1. This case is not singular. So you get one I ordinary, let's say, contribution, which in fact reduces to one with bubble integral that we calculated earlier. So this you simply set y equal to 1. And then there is this sort of singular contribution that you can achieve by the following scaling. So you again introduce alpha and beta as a bound. And now the scaling is slightly different. In particular, the novelty is this effect. Oh, I think it's like this. Could be the other way. It's not really important. The issue here is that this is what I was hinting at earlier. In the singular region, it's important to give an non-trivial scaling also to T3, essentially because it enhances this term here that involves the velocity. So the right scaling to consider is the following: 1 over tau squared alpha is like 1 and beta and tau. I'm slightly confused by one thing, but maybe I will think about it during the break. So if you do this, you can see that the integral with respect to x1 and x3 is very, very similar to the one we just did, and then you can actually evaluate exactly the integral over T1, T3, and T1, T2, and T3. So this singular region is actually simpler than the other one. But the technique is really the same. Okay, any question? It's a bit technical, I apologize, but I just wanted to give one at least hint of a not exactly trivial example like the box. Yeah.
So just to check if I understood, so first you evaluated the box by, let's say, the usual means you just evaluate the integral.
Yeah.
Okay, and then in the second part you evaluate it using this system of differential equations. But so actually method of region only enters for boundary conditions.
Eventually, yes, in the sense that the first one is just a justification that you say at the beginning. We are just interested in the soft region, and then you expand it in this. So in principle, also here, right? You would have u1, and then in the true integral you have plus L1 squared, say, for instance, right?
Okay.
So here I'm not putting it because I'm already considering the soft region with respect to the limit q goes to 0. Which means that L1 and L2 also scale like Q, and they are much smaller than the masses. And then you never even consider the hard region for these applications. And then exactly, there is another application of the method of region when you go to the boundary condition.
Okay, but for the box you did, so there was only one appearance of method of region just for the bound.
No, at the very beginning when I tried to describe what the method of region is, you remember there was a box with the L squared in the denominator.
So
and
you
then
already set it. Okay.
Exactly. So what I'm not computing is the hard region for the box in which you leave the L squared and neglect the Q. So yeah, there are two places in which it is.
Okay. Thanks.
Okay.
For the box, regional box integral, wouldn't be simply just to look at the special representation.
Yeah, in a sense, it's not very different than what I did in the end, right? In order to divide it by this maximal cut or two particle cut, this is basically using unitarity. So yeah, it's very similar.
Especially if you look for imaginary pattern.
Exactly. No. In the end, you see this is why I didn't want to show only this, because this essentially is too trivial. You can do it in so many different ways. Then you say, why bother? Then okay, one answer to that is that, for instance, for these higher loop examples, it seems to be a bit easier to organize the pipeline in this way, although it's still very challenging. 3 loops, for instance. If there are no further questions, we will reconvene at 1/4.
Thank
Because in principle, there is another topic that I wanted to present, but to some extent is a bit of a repetition of some things that we already discussed in a slightly different language in the previous lecture. So, and the issue is that the last 2 lectures then would be very dense. So then I think I will present quickly the punchline of what I wanted to say in this sort of chapter, and then if you have questions, I can refer you to a more detailed discussion that is in this physics report, or you can come ask me, of course. So as a quick excursus, let's say, to briefly mention the difference between phase shift or the radial action and the igonal phase that we talked about in the first few lectures. Just because it's a topic that sometimes is relevant when you're reading the literature and can be a bit confusing at times. So the key idea is is the following: that you remember in the iconal setup, we were taking this impact parameter Fourier transform of the amplitude, particularly of the 2 to 2 amplitude, and then identifying this as an exponentiated form, which can be shown to be correct first few leading orders, and sort of keep believing that. And instead, in another possibility that is, of course, very, very interesting is to, instead of performing this Fourier transform, perform an exact decomposition in terms of energy, angular momentum eigenstates, so to go to so-called partial waves. Well, maybe the parallels should be following. The phase shift is what you get when you go, so here is the Fourier transform, and here instead you go to partial wave. So essentially, we write the whole amplitude, say 1 plus I, what, 2fj, where j now is the new label instead of being v. This is really the angular momentum, and we identify this as e to the 2I delta j. And then in principle, it will also quantum remainder. Let me not give it a name for the moment. So these fj's are defined by really going to angular momentum, which means instead of projecting with respect to a plane wave, means projecting with respect to a Legendre polynomial. So let me give the precise definition. Fj is p divided by 16 pi e, integral from -1 to 1 d cos theta pj, Legendre polynomial, of the amplitude. And then instead of evaluating it at q, we evaluate it at q squared equal to 4p sine of theta half. Readable. Okay. So the reason why this is a good idea is the following, namely that partial waves. So here I'm focusing on massive scalar states, so the ones that are the focus of the whole course, actually. And the key property that these partial waves satisfy is that they exactly diagonalize the two-body convolution. What do I mean by that? So you remember we had this unitarity equation. Then what one can show is essentially a consequence of the Wigner-Eckart theorem, if you want, is that when instead of taking initial and final momentum states, eigenstates, and then taking the Fourier transform, which is what we did in the last lecture, you do the same initial and final momentum eigenstates and do the partial wave expansion. Then what happens is that the bound, the identity that you derive is that the imaginary part of fj is equal to fj squared, with value squared, plus contribution that comes from the inelastic channel. So you remember, we had a 2-particle cut, 3-particle cut, and so on. What partial waves do for you in a nice way is that they exactly diagonalize this integral over the two-body phase space. Instead, you remember last time we discussed also with some detail the fact that this Fourier transform doesn't exactly do that. It does that to leading order for large B, which is equivalent to large J. But then it receives this, the Fourier transform of this is not just the product of the Fourier transform of the two blobs. It also receives corrections that are sub-leading in 1 over B. Instead, no. Here, the benefit of going really to partial waves is this diagonalization is exact. So in particular from this, you can easily deduce some famous bounds. One of them is the imaginary part, of course, is bigger than f squared, simply because all these inelastic things will be positive. And well, there are several others, I do not dwell too much on that. the point I wanted to emphasize is the fact that the iconal phase and the phase shift are the same at leading and subleading order, but start being different at sub-subleading order. And yeah, I mean, the reason why I don't want to go through this in detail is because it would essentially take my lecture today to really show in all the steps. But maybe let me just write down the punchline. So you remember this delta has a 2 delta 0. So for simplicity, let me stay in D equal 4 because this is really the partial wave decomposition in D equal 4, of course. Otherwise, one should use Gegenbauer polynomial. And to regulate the Coulombic divergence that is in delta 0, let me replace it by just so practice the statement that the part of the delta is delta 0 except for this replacement plus delta 1 plus delta 2. And then in the classical limit, and in this large B or large J approximation, the relation between the iconal and the amplitude, so the amplitude, of course, is the fundamental object from which we start, so A0, plus A1, plus A2, blah, blah, blah. And then we can either perform the Fourier transform, so put a tilde on this, or go to partial waves. So the final statement is that if one does a similar expansion for this exponent here to delta J, in order to make it apparently they are not the same, let's introduce another symbol. Let me call it chi, just because so it depends on the classical angular momentum. This is also going to be phi 0, phi 1, phi 2, dot dot. So chi 0 is equal to 2 delta 0. Chi 1 is equal to 2 delta 1, simply because these sort of spherical aberrations that are such that this two-particle convolution is not negligible, sorry, is not factorized, are irrelevant at leading and subleading order, but at next leading order there is a difference, and the difference is okay. The real part of 2 delta 2, you remember the iconal is evaluated in terms of the iconal impact parameter. Instead, the angular momentum is more naturally related to Bj, right? Which is orthogonal to the incoming momentum. So P times Bj is the angular momentum. So the real part of the two-loop iconal that you derive from the amplitude, evaluated in B replaced by Bj in order to make the comparison possible, minus the real part of this I2, so the two-loop phase shift that you define from the partial waves, the function of J, it's not 0, and is precisely this quantity here. This is one of the punchlines. The other punchline is that is about what they mean for physical observables. You remember the iconal was such that the momentum impulse or the deflection angle, if you prefer, are related in this way. Here I could put the real part. Okay, instead the phase shift is such that directly the angle is minus the derivative of the phase shift or real part of the phase shift with respect to the angular momentum. So these are different relations. And you can check as an exercise that this difference at order next to leading order is precisely such that these two relations give the same reflection. So to summarize, at leading and next to leading order, you don't care. At next to leading order, you start having to care in the sense that the amplitude is the same, unique. Then what you do with it, so either take the Fourier transform or the partial wave decomposition differs, and the result is that you get two different exponents in these two stories. One is the iconal phase, and the other is this phase shift. And then they are related in a slightly different way to the observable, the deflection angle, and the difference between the two is precisely such that you get the same deflection angle. This is a bit. Any question? remark. In fact, one way in which you can show this relation is precisely by taking the result amplitude momentum space, going to transform in order to, sorry, you start from the factorial amount. You resum it in this space, you go back to momentum space, then you can apply this formula to calculate the phases associated to the resultant amplitude from the iconal, and you will find that the relation is such that this is. So everything is consistent. Okay. And now what I wanted to do is to switch gears completely in this last half an hour and start talking about something completely different. So remember two words of the title of these lectures didn't just have to do with amplitudes and gravitational wave observables, but also with these soft effects and BMS. So this is what I wanted to talk about. So the idea is that all our scattering processes are gravitational interactions between objects that are localized. So for instance, there are two massive objects with some Schwarzschild radius, or neutron stars that interact in some portion of the bulk of the space-time, so they have some sort of world tube. Could be very large if there is a scattering, but let's say, for instance, let me take for simplicity, just for drawing it in a simple way, the scattering of two, so the merger of two massive objects, they will orbit around each other, so they will evolve in a world tube. So this is a 4D diagram projected in 2D, of course. And I mean, and the idea is that they stay in a fixed region, and far away the field reduces to the flat gravitational field. Of course, in the meantime, they emit gravitational waves, but these die out with some fall-off for large distances. So our interferometry experiments just measure a signal which is very, very small. In fact, it's one of the problems, very small. And and people in the 60s, particularly Bondi, Metzner, Vanderburg, and Sachs, developed purely from a general relativity perspective a formalism to describe these classes of spacetimes which are called asymptotically flat. Spacetimes. In fact, I presented a couple of mini lectures 1 year ago here precisely on this topic. So what I wanted to do, although I'm sure nobody will remember, but I wanted to present it in a different way than the way I presented it at that time. So the key idea of these original papers is to introduce some retarded time, which is measured by the asymptotic observer, U, a radial distance, which is more precisely a luminosity distance, R, that tells you that you are very far from this phenomena, and two angular coordinates, θ and phi, that tell you at which point on the celestial sphere, so-called, you are with respect to the source, and discuss precisely these large R fall-offs for fixed U, θ, and phi. So in order to characterize how fast the gravitational field decays very far from these sources, again, just from a pure GR perspective. Let's forget about amplitude for the rest of this talk. Instead, let me introduce this topic in a slightly different way. Let me start from flat space. Which are all very familiar with. This is our beloved Minkowski space. But we are going to write it in coordinates that resemble these choices over here. So some retarded time and some radial distance. And with respect to our with respect to x 0, 1, 2, 3, of course, this is the mapping, and θ and phi as usual. Particular gamma ID for the usual θ and phi will be 1 sine theta squared. But in general, if you choose some different coordinates on the sphere, it's up to you. You can, for instance, introduce some stereographic coordinates like cotangent of theta, e to the plus or minus I prime, call them z or z bar. Again, it's not important. The idea now is to try to see what happens very far away from the origin, although flat space-time is a bit boring, nothing is there. But suppose we want to fix the origin in some way, and then try to describe the geometry very far from it. So let's try to do that. We introduce another coordinate, omega, which is 1 over r. And then multiply the s squared by omega squared in order to have a nicer limit as r goes to infinity. So we define some g tilde maybe, where this instead was GAB. And this time minus omega squared du squared plus 2 du d omega plus gamma. So this is just a change of coordinate, and then we multiply by this conformal factor omega squared. Now the idea is to so basically what we did was to go from our space-time to another space-time, an unphysical space-time. This would be a physical space-time. To an unphysical space-time in which we multiply the metric by omega squared. But the benefit now is that what we can do is we can really set omega to 0 and see what happens. So in particular, we can first restrict to a surface of fixed r or fixed omega. Let me call this sigma omega. So this simply means that this term is not there because omega is fixed. Okay. And then when we want to really go to r equal to infinity, which will be the boundary of this unphysical space-time for fixed u. So basically really taking this limit following a null direction towards infinity, we get, so omega tends to 0. We get what people call the metric on the so-called future null infinity, which I'm calling this calligraphic I, or sometimes it's called scry plus, which as you can see is 0 times the u squared plus just a metric on the sphere. Gamma AB dx dx. So, so basically what happened is that in this sort of toy space-time, we can really define a metric on the boundary. So we can make precise the notion of going to infinity, and this turns out to be a null surface, maybe not surprisingly, associated to the future. So what one does, I'm not sure how many of you are familiar with Penrose diagram, but this is just a drawing to have in mind some image when thinking about this procedure, which is only and just attaches to space-time. I mean, literally a boundary. So we draw a line, and the convention is that since we are doing a conformal rescaling, angles are the same angles as in the physical space-time. So if something is null, it should be at 45 degrees if the speed of light is 1. So this is going to be our unphysical space-time. And then, of course, there will be a similar procedure to discuss what happens when instead of going to future null infinity, you go to minus to past null infinity. The correct drawing to assign to flat space-time is this one, in which this is our straight plus, and then there will be a straight minus that I'm not really discussing. And then, of course, you can complete the pictures by considering what would happen if you went to infinity, but just following a time-like direction. So, for instance, if you stand still, you will end up in something that is here. Or if you said go to infinity in a space-like direction, you will end up similarly. So this is just flat space-time mapped in some contorted way in this physical thing. What do we gain? I will answer this question in a second. Before doing that, let me introduce another piece of information. So another interesting object is instead of the metric on this surface, is it normal, the unit normal associated to it, which is simply n tilde A is G tilde AB BB omega, right? Because this is a surface at fixed omega, so the normal is just the gradient of the constraint that defines it. And so for instance, if you want, we can write it in a more mathematical way as a vector field in this way. And if you do the algebra, so you invert the metric in order to get the metric with the indices upstairs, you find du plus omega squared d omega. And again, as omega tends to 0, we find the normal to scri at scri, which is just du. Okay. So the key idea that people have, which is eventually equivalent to this characterization I was hinting at by the original papers, is the fact that asymptotically flat spacetimes are those spacetimes such that there exists a conformal mapping to an unphysical spacetime whose boundary has the same two pieces of geometric data attached to it. So this metric here, this null or degenerate metric, and this unit normal. And there are two important take-home messages. The first is that metric is is proportional, so it has the topology, this boundary of a line associated to the retarded time times the sphere. So it's just a fancy way of saying that asymptotic detectors measure for some time and receive signals from different angles, so time and two angles. And there is a null direction which has this associated normal. However, there is some ambiguity in the way in which I perform this mapping, right? You remember, eventually, the only important piece of information is the fact that omega goes to 0. So it doesn't really matter if I choose omega, capital omega, or capital omega times a function that is regular at the boundary. So ambiguity or freedom. Suppose I redefine omega times capital omega as capital omega times lowercase omega, provided that omega is smooth, particularly it doesn't diverge, otherwise it no longer diverges, of course, but could no longer diverge. So then what happens? Well, the change in the asymptotic metric is it is still 0 times du squared. This doesn't change, but then you have a factor omega squared. In the metric, and the unit normal, as you can see from here, is that as a factor of 1 over omega. Yeah.
Why do you keep 0 answer
Just to remember that this is a metric defined in a three-dimensional space with the retarded time and two angles, but it has a null direction. Yeah. Of course, you could just drop it.
What's the meaning until there?
Yeah, tilde is associated to things that live in the unphysical space-time. For instance, the original metric was the G without the tilde. So the flat.
What's the meaning of this very first relation? What's the meaning of this until the A vector?
Yeah, and tilde is the normal, the unit normal to the surface, right? For instance, if you have in general, if you have a surface defined by f of x equal to 0, some constraint in your space, then the gradient is you can just define it in this way. And the reason is that every vector, if you take a variation of this relation, you will find something like this, right?
Okay.
You do x plus psi. So then tangent vectors are orthogonal to this thing, and this thing is the gradient. It's the thing orthogonal.
It's like wavefront, direction which wavefront.
Exactly. So then, okay, this is in Euclidean space, which orthogonal things are actually orthogonal. This is a null vector, so it actually exactly, is aligned because n squared equal to 0. So something squared equal to 0 can both mean that it's an orthogonal in the real sense, but also a null.
But this
Aligned.
teach below pictures will be teach you through. So it's just direction will be.
Yeah. This is you see, du is really exactly the direction along the retarded time of the observer. So it's really pointing in the. I mean, observers cannot really stand still if they are actually null, but if they could, it would be their proper time, which they can't have. You get what I mean. Okay, so this was all to say that there is an ambiguity in the definition of this asymptotic frame, in a sense, this asymptotic surface, and this, as you can see from here, is just an ambiguity with respect to a conformal rescaling of the metric and an associated rescaling of the unit normal. And it's actually a kind of cute exercise that maybe I can do to actually solve and find what the most general space of vectors associated with this transformation is. So let me try to do that. So suppose we perform a transformation u prime equals to some f of u and x. So collectively, I will denote x1 and x2 of theta and phi as x, and x prime as g prime a as ga of u and x. So this is a mapping of this scry onto itself, and we want to impose that it satisfies these relations. So let me start on the second one. So di prime, then du prime is going to be duf du prime plus duga k prime. And in order to impose that, it should be equal to omega du prime, because sorry, no. This is du. Okay, that makes more sense. And then this should be equal to omega du prime, because I swapped the two. And now from here we can read off that well, du of f should be equal to omega, and du of g prime should be 0. G. Okay, just comparing the independent direction. Now the more precise form of this conformal transformation is the following. Usually it's very easy to get confused with primes and non-primes. Let's hope that I get it right. dA GC x. Now we know that it does no longer depend on u. Gamma, the same metric, so gamma without any prime, CD, calculated at x prime, d d g d x. So from this relation, which is just the conformal rescaling over there, we see that omega cannot depend on u because nothing else depends on u. This is another constraint that we get. And therefore, in particular, from here and here, you can go back to here and deduce, maybe, okay, let me do it in another block. Not in another. So, where were we? Okay, from these two, we can go back to the first relation and use the f. So, the derivative is omega, and omega does not depend on u, so it must be u times omega, or let me call it u times r, later convenience. And then an integration function, let's say, that does not depend on the retarded time. And okay, the rest is simply that GA is the conformal transformation. It is a conformal transformation. Let me not solve the problem of conformal transformation. So the punchline is that GA is a conformal transformation that does not depend on U. with R as its conformal weight or conformal factor. With R squared as its conformal factor, and F instead is a, let's try to interpret it, is okay, it has U times R, which is in a sense is a sort of a time dilation, right? Because the conformal factor stretches the retarded time of the observer, and T is a sort of time translation, right? If it was just F equal a constant, it would mean that U goes to U plus a constant, so it would be literally a finite time translation. However, this is a time translation that depends on the angles, so you can think of it as sort of let me try to do draw a picture here. Suppose you have some light front that, or gravitational wave front that reaches the observer sitting here, and in one frame is supposed to reach it simultaneously, right? U equal to 0, for instance. Then what these transformations do is that they deform this a little bit in a way that depends on the angle. And this kind of direction-dependent translations are called super translations. Instead, these conformal transformations, as we're all familiar with, conformal transformations in for a two-dimensional sphere, the only non-singular ones, are actually isomorphic to the Lorentz group. So indeed, these are 6 independent transformations that correspond to rotations and moves. Okay. So, and in fact, the same result had been obtained by the original Van der Burg, Metz, and Sachs approach, in which instead of using this sort of formal geometric way of thinking, they had instead, as I mentioned, solved the equations of the Einstein equations asymptotically for large R at fixed U and X, and imposed them in order to find that there are non-trivial solutions associated to gravitational waves in particular, and studied the mappings that transform this space of choices of coordinates and of solutions to themselves, and they find the same set of transformations. Yeah.
Yes. So you start performing this transformation U prime X prime.
Yeah.
So you impose some conditions on those functions on G.
Yeah.
In order to achieve what?
To preserve these conditions, right? You remember these two pieces of information, so the metric and the unit normal, came by this mapping from the physical spacetime to the physical spacetime, and the only thing that we care about in this mapping was that it mapped us to a smooth boundary, so that when we set omega equal to 0, we find a non-trivial metric, okay, degenerate because it's null, but it's non-trivial, and that was the only thing we care about. Then we said, okay, but suppose we do this mapping in a different way, by rescaling omega in this way, like by another small omega, which doesn't affect the behavior for large omega. I mean, it's still omega is still 0 in the still the same set of points. Then we see that this change in this way. So then we are looking for the transformation, the intrinsic way of performing this transformation on the surface, right? And this means a mapping, a local change of coordinates of U and X that preserve these two conditions.
So you're talking about general coordinate transformation, which preserves this behavior at infinity.
These two conditions. The behavior is sort of implicit in the fact that U theta and phi go to U prime theta prime and phi prime. They're in the same. They are coordinates in the same surface. And the additional condition is that they preserve these two conditions.
The resulting group which you write is
exactly this
possible translation.
Exactly. This is an enhanced version. Is a Poincare on steroid. It's the so-called BMS group. So let me. This BMS is SO3, 1, and instead of having the semi-direct product the semi-direct product with respect to R4, so translation, it has this super translation, which include ordinary translations as subcases. In particular, the constant would correspond to a time translation, and the two choices for sin theta cos phi, sin theta sin phi, and cos theta correspond to the space translations.
If I didn't know about this, I start with like four-dimensional space-time.
Yeah.
And I know I have conformal group, which is SO2, SO4, and then I impose on my space-time some hypersurface. I basically just use this non-infinity, and I require that my transformation, my full conformal group, should leave the surface invariant.
Yeah.
This will be.
Yeah, I think it's the same result. In fact, more recent papers have shown that you can, by playing around with geometric conditions, you can actually place this surface more or less anywhere. Here, it's particularly well motivated to use it at infinity because we care about gravitational waves, but I think you're right. It's yeah. So the last thing I wanted to do today, so we might actually go lunch earlier than usual for once, is to tell you how the metric transforms under these super translations asymptotically, because we will need it next time. So again, the right thing to do would be to write down the asymptotic expansion of the metric, and derive super translations by imposing they preserve the Falloffs, and find not only the super translation but also the transformation rules. Here I'm as I mentioned, I'm using a backward approach. I'm first working exactly on the boundary, and then what I want to do now is to extend back my calculations a little bit inside the bulk, or more precisely inside the bulk of the physical space-time. Remember, this is unphysical. And then I want to go back to the physical space-time. So basically what I'm trying to say is that, of course, these transformations will simply leave the flat metric invariant. Suppose we now have the flat metric plus a perturbation. What is the transformation induced on this perturbation, which is essentially how does the gravitational waveform transform? So in order to do that, let me make an answer for the form of this potential. So what one gets from this BMS analysis, although this is not very important, but I just wanted to mention, is that GUU will be -1 plus something that goes to 0. GUR is also -1 plus something that goes to 0. So they are small perturbations of the flat metric that you had, that we had earlier. GUA is small, and GAB, of course, is R squared times the metric and the sphere, plus something that is small with respect to R squared. So let me call it RCAB. We assume a power law behavior. There is a whole literature on trying to include logs. Let me not dwell too much on this. And then something that goes here. So what we care about is guidance. To do that, let me, as I was mentioning, make an answer for the super translation. In particular, we care about super translations. So Lorentz transformations, we know how they work. People have also tried to consider singular generalization of these, or even further generalization, but these are sometimes called super rotations, but not again. Let me not go in that direction today. So the reasonable answer is that they will generate a translation that is weighted by this t when they are exactly at square plus. Then we want to include something else, which goes away when you restrict to square plus. So in particular, some r direction and some dA direction, which is subleading, so 1 over r plus dot dot dot. So these now are extended away from square, and then we can find psi r and psi a by imposing the following conditions. Maybe I can try to do it. So the first condition is that they should preserve this GAR equal to 0, which is forgotten, right? Yeah, so GAR is 0. and also the determinant condition, which essentially imposes the metric, imposes that what I'm calling R is actually luminosity distance, gamma being the determinant of gamma B. So the first condition is delta psi dA equal to 0, and the second condition is going to be essentially a consequence of the asymptotic Killing equation, right? The asymptotic Killing equation would be the covariant gradient of psi symmetrized equal to 0. A consequence is that its divergence is 0, or more precisely, -0. So we're going to impose these two conditions. In fact, there is a nice discussion also involved about the fact that you can actually see this condition by starting from our scry, extending the coordinates slightly away from scry, and then going back to the physical space-time. The two procedures are completely equivalent. So the first condition, the one over here, would be psi. Well, there will be one term that is psi a, sorry, dA psi r, sorry, psi u plus r squared gamma b dr psi a. This just comes from expanding this will be the lead derivative, right? And okay, from here we can substitute our ansatz, and we find we can express psi a in terms of psi u, which would be this guy. So you see this is related to a derivative of this function t, the minus sign. So here it doesn't matter, but for later let me use this dA, which are the derivatives, the covariant derivatives on the sphere. So if you want the Christophel-Sims with gamma A, B, C, 1/2 gamma A, B, D, B, gamma B, C, plus. Yeah, but for the scalar recording, it doesn't matter. It matters later on. And the other condition about the divergence is u psi u plus dr 2 over r psi r plus dA psi a equal to 0. You can use it on the same order one. And okay, the result, you substitute this ansatz again, and now what we gain is that we can express psi r also in terms of t as follows: 1/2 Laplacian. Well, the Laplacian is defined with respect to this. With respect to the sphere. Okay, so finally we have our Killing vector, or asymptotic Killing vector for supertranslation. U minus 1/2 r over r dA dA. Simply substituted this into psi r and the other psi a. And the last exercise is now you can, so this is the infinitesimal supertranslation if you want. And then you can use this vector, take the lead derivative of the metric in order to deduce how this CAV changes under a supertranslation. This is again a simple exercise, so let me try the variation of this CA, which follows from the lead derivative of this. And okay, the interesting bit is the fact that you find not only this piece, which is, I mean, we could have guessed, right? If we are doing a super translation, which is just a time-dependent translation with respect to time, so the infinitesimal time translation will be t times the derivative with respect to time. And then there is a sort of non-trivial bit that comes from the lead derivative, which is a sort of gauge transformation, right? In the sense that it's non-homogeneous in the field that we want to transform, and depends on this parameter, which is sort of a gauge parameter. Although, yeah, the emphasis, at least in the GR literature, but also in the more recent literature in connection with soft theorems, is that this transformation should not be regarded as gauge redundancies, because they act non-trivially on the asymptotic data, in particular on this thing, which is precisely the metric. This is, I mean, the two independent components of this guy. There are only two, because the determinant condition restricts this 2 by 2 symmetric matrix to have to be traceless, essentially. So these are really the two physical parameterizations of graviton, plus and minus, or positive and negative helicity, if you want. And they act non-trivially also on the waveform, although I would say the physical observability of this effect is still a bit unclear. So but I wanted to present this in some detail because it will be important next time and also for the last time. Okay, I think we are done for today. Any questions, comments, complaints, wishes?
Sorry, this, it's ready to go to physical logic. I mean, this said that it's actually Penrose's limit when you take this null geodesic to infinity. It's
Yeah, I mean, the name is the same, so Penrose diagram. That's probably
diagram.
No, I know, I'm joking. I see what you mean. I think it's a similar idea, but it's I mean, I'm not really very familiar with the Penrose limit for geodesics, although you explained it to us in our last journal club. But I mean, as far as I get, the idea is similar, but the implementation I think is slightly different.
Yeah.
Because you're applying it to the whole surface. There is you're following a geodesic. I mean, maybe it's a bit different. Maybe it's just a taste. No. I mean, it sounds similar in the sense that you're taking a asymptotic limit close to a n minus something dimensional surface, then the details escape to me about.
Because in general, this say the Penrose diagram is the conformal transformation of the metric.
Yeah, exactly. That's what we did, right? We multiplied omega squared, the whole metric by omega.
There is also rescaling.
Exactly. So in the Penrose limit, there is rescaling of the coordinates.
Yeah, I think Filippo is right. There are different rescaling of different coordinates. Here instead it's an overall thing. That's already different. I mean, in a sense, it's because you are zooming in also here on the boundary. I mean, the boundary is infinitely far away in the physical space-time. So what you want to do is to bring it back to a finite distance. So it's as if the eye you are zooming away on the boundary, and then of course whatever happens in the bulk is deformed in a very complicated way, but you don't care because you only use it as a device to describe the asymptotic structure and then go back to the physical space-time at the end of the day. Also, I should emphasize that this approach is actually not very nice in odd dimensions, because for mathematical reasons you have to assume that these things are smooth, etc. But in odd dimensions you would have half odd powers of this scaling that matter. Essentially because the metric goes like 1 over r to the d minus 2 over 2 instead of being 1 over r for the radiative mode. So d minus 2 over 2 is odd in odd dimension. It is half odd in odd dimension. But there is again a whole literature on that. It's a bit too much for today.
Other questions? Also from the virtual room, if you want, you can ask questions.
Okay.
So
No,
thank
then
you.
see you tomorrow.
Yeah, so the next lecture will be on Monday, next Monday, at 15 past 2.
Yeah, in the afternoon.
Because Why?
Yeah, I will need to be away next Friday.
What we do?
And I will discuss a bit the soft theorem and the application of the soft spectra and the connection between the memory and